How many folks in here are knowledgeable about TensorFlow? Okay, so some of you folks have probably explored these doc sets to some extent. I found them challenging to navigate, and so another one of my goals here was to sort of boil things down for you and really choose the pieces of these docs that I found important for understanding this end-to-end workflow from Earth Engine to TensorFlow.
Also throw in the tip I threw in at the last section. If you're looking for something in TensorFlow, it may or may not have 3 different aliases. So if you're looking for a 2D convolution, it'll be called conv2D convolution, then conv2D with a capital C. And only one of them will actually have the docs for what they all do. So if you can't find what you need, look for things of a similar name, and that can kind of help sometimes.
So we're going to be doing all this in Collab. And Collab is a cloud service that's integrated with your Drive account. And one of the nice things about Collab is that well, there are a bunch of nice things. It's connected to your Drive account. You get a free virtual machine, so you don't have to enter your credit card and that kind of thing. It has the TensorFlow library already installed, so it's a really easy way to get up and running quickly.
And it's GPU accelerated.
There are a lot of good features of Collab, and so that's what we're going to be using today. This is the symbol to get started with the hands-on portion of the course if you're interested in following along. The first thing that we're going to do is we're going to get you hooked up with Collab. So everybody please go to your Drive account. Oh, and let me just mention, previously we had some issues with authentication, and often that's due to the fact that folks are logged into a whole variety of different accounts on their machines. And so let's try to make this smoother. It'll be best if you use one account for everything. You know, whatever your account is for Earth Engine, let's use that for everything, because otherwise files are going to be going to different Drive accounts and you won't find the things that you need and confusion will ensue. So go to whatever Drive account it is that you're going to use for the rest of the course. Hopefully it's the same account that you used to log into Earth Engine. And click the New button. And once you click the New button, you'll see a little menu here. And the menu will say Connect More Apps. Hopefully it'll say that. So you click that. Search for Collab. And hopefully find Collaboratory. And click the blue Connect button. And hopefully that will take you to something like this. And you click OK. Did I lose anybody right there? And now, when you click the New button and More Apps or something like that, you should be able to see Collaboratory in the menu there. Is anybody having trouble with that? If anybody is having trouble at any time, just raise your hand and one of our TAs will assist you. Okay, so you can make your own Collab notebooks now, but you don't have to do that because we have some notebooks that are prepared for you. And so here's what we're going to do. You have the slides. Hopefully you have the slides. If you don't, the link is on the whiteboards in the back, or it's right here. So first thing is to get the slides so that you have these links. Join this group. When you join it's a public group. Anybody can join. So you join the group. You might see a message that says something like, you don't have permission to post topics, or, you know, never mind that. You just have to be in the group. The other day I got a whole bunch of emails, you know, please let me into the group, from people who are already in the group. So you do not need to email the owners of the group. You just have to join, and once you join, then you're in. The reason I want you in that group is because I have shared this notebook with the group. So I also got a bunch of emails the other day, please give me access to this notebook. You don't need to do that because once you're in the group, then you'll have access to the notebook.
Also the cloud storage files, right?
Yeah, and there's a bucket. We have a temporary cloud storage bucket that group has write access to. So if you want to follow along, you need to be in that group. Rather, yeah. If you have your own cloud storage bucket, that's okay, but then you have to change parts of the code in various places to use your own cloud storage bucket. But that's the idea of these notebooks that we're giving you, is that you can change the little pieces of the code to use your own stuff. Is anybody able to get the notebook? Okay, once you have the notebook, file, save a copy in Drive, and then you will have your own copy of that notebook, and you can run stuff and change stuff and so on and so forth. Okay? All right. Please raise your hand and someone will help you. And it may be groups settings, in fact, Marissa. Your groups, you might have to fiddle with your group settings. I don't know. Okay, what are we doing? So what are we doing? So the dashed line on this diagram refers to stuff outside of Earth Engine. So the idea here is that you've got some image data from Earth Engine, and what you're going to do is export it. So we're going to export training data and testing data as tables to TF record files. We're going to use those tables to train and validate a model in TensorFlow, an estimator model, specifically a deep neural network, or DNN estimator, I think it's called. Yeah, a DNN thing. And we're also, at the same time, we're going to export some image data to TF record. We're going to use the trained model to predict on the image data, write a new TF record file, and upload that back to Earth Engine. And all this is going to happen without ever touching your machine. So the idea is that you're doing this completely in the cloud. And I told Chris that my goal here was to be able to do this on the bus with my cell phone connection.
And for free,
yeah,
which is true.
For free on the bus with my cell phone connection, meaning that I'm not uploading and downloading big data sets here. It's all happening in the cloud. Any questions about that? Okay. So, as I said before, we're going to be making data sets, and specifically, we are going to be making TF record data sets out of data from Earth Engine. So let's get started with that, and I am going to go to my notebook, and you should see something like this. That's a little too big. How about that? Is that readable? Sorry? That okay? All right. So here's a Collab notebook, and is anybody unable to get to this notebook? Okay, is anybody able to get to the notebook? Are the people who are unable to get to the notebook in the group? I don't know. Sorry. Chris, maybe you can help with triaging a little bit here. If you're still having trouble, please raise your hand. Okay, here's the notebook. All of y'all should have access to it, so whether or not we work this out right here and now, that's okay. The slides are going to be online. You'll all have this notebook eventually. this is a Collab notebook, and one of the really nice things, so Collab notebooks are these Jupyter notebooks or IPython notebooks hosted on this free virtual machine provided by Google. And the nice thing about these notebooks is that you can sort of mix text with code with images and links and so on and so forth. If there are any Jupyter people in the house, please don't just run all cells in this notebook. That is not going to work. We are going to step through the notebook, and just please be patient. We'll get to the good stuff eventually, I promise. So the first thing is you just click on this code cell here, and what should happen, fingers crossed, is that when I click the run button, so I just clicked the little run button here, and what we should have is that this will complete successfully with no error, and then it'll tell you the order in which these code cells have been run. And if that runs without error, then we're good, and we've imported the TensorFlow library. So one of the nice things about Collab is that TensorFlow is already installed on these virtual machines. So, yeah. No, but we're going to install it later. Okay, so the first thing that you do in any programming language is hello world. And so the way that works in the TensorFlow world, no pun intended, is, oops, it's annoying, that you create a constant tensor, which is just a string, and the string says hello world. And the TensorFlow execution model is somewhat similar to Earth Engine in that it is a deferred execution model, which means that nothing happens until you ask for it. And the way that works in TensorFlow, there are new ways of doing this. And well, there are several ways of doing this, including new ways that we're not going to cover. This is the sort of the old school way, is that you do everything in a session. And so you create a session, and then you say session, run that variable. And when the session runs the variable, it evaluates what it is, and it's just hello world, and then it prints it. Is anybody able to get hello world printed into their notebook? Good. Okay, any questions about that?
This thing is for running the cloud.
Yes.
Train will run
All of it.
any means to know the signature. Any means to know
How much CPU, GCU you're using?
if we are like running out of memory or
So in the free version of Collab, no. You can connect it to a managed instance that I believe you have to pay for if you want to have metering and multiple GPUs or anything like that. But in the free version, no. Just last thing I'll say on that is you'll have to work pretty hard to break it. It took me about 2 hours of training to get blacklisted from using a GPU. So on a continent, yeah, that's fine. Yeah.
Other questions? Okay. The next thing that I want to show you is installing libraries. So note that if I run this cell here, so I'm on the install the PyDrive library, and what I'm demonstrating here is, first of all, the exclamation mark, which tells the notebook to run a bash command. So we can say exclamation mark pip install PyDrive, and that will install a library that will give us access to your drive files. And that's nice because then you can do stuff like export stuff from Earth Engine into your Drive account and then pick them up from there and load them right into this notebook. So we just installed that library. And now what we need to do is some authentication. So we want to authenticate you as you. So we can see your drive files, and you can use Earth Engine. Well, there's another authentication for Earth Engine later, but we want to authenticate you as you for the cloud storage bucket and for your drive files. So we did these imports, and that should run without error. And now, when I authenticate, what's going to happen is, hopefully, we'll know more soon, you get a little link like this, and I'm sure many of you have seen this before. You click the link, it takes you to this thing. Yes, I am N. Clinton, and yes, I want to allow all that stuff, and if you want to follow along, then you need to allow all that stuff. Of course, it is entirely up to you, but you do need to allow that if you want to follow along. So I just got this entire code here, and I'm going to paste it back in, and I'm just going to press enter. So I just pressed enter, and now I'm authenticated as me, and I can throw this out. This is not useful anymore. And now we should be ready to go. Again, raise your hand if you have trouble. Okay, now we have a link to the code editor here. And I am doing it this way because I want you to see I want you to see this little map here. We could have done this entirely in the Python in the Collab notebook if we wanted to, which would be a little bit fancier because then everything's in this notebook. But unfortunately, the Collab doesn't have the fancy slippy maps and other widgetry that Tyler's demonstrating in his Python session. But we have TensorFlow and all kinds of other goodies. So what we have here are some training points. And these should not be considered a scientifically valid data set in any way. This is just for demonstration purposes. These are points that I have made by hand with visual interpretation of this composite and may or may not be correct, but these are points that I made in Earth Engine. And all we're doing here, there are a couple things we're doing. First, we're getting, so this is a composite, a cloud-free composite. We're getting the pixel values at all the points. We're going to partition the points into training and testing and export them. We're also going to grab the piece of the composite that's in that box, the blue box there, and we're going to export that as well, and that's what we want to classify. Okay, so that's it. And if you look into the code here, what you'll see is a bunch of exports, and I've commented the export .table.to cloud storage because I'm sending those to this cloud storage bucket, and there's no need for all of y'all to run those same exports and write the same files into this cloud storage bucket over and over and over again. I already did it. They're already there. Don't worry about that. On the other hand, these table exports are going to your Drive account. And the image export is also going to your Drive account. So everybody should run these exports. So please do run the exports, especially the image. You will need that image to be in your Drive account for later. The new thing here is that when you run this, you should see something like a new format TF record. Another thing is, please do not change that file name at all. If you change the file name, that's going to break some stuff later on, because I have that file name hard-coded into the notebook. And again, if we were doing this the fancy way with all the Earth Engine stuff in the Python notebook, we wouldn't have to do that. We'd just name the variable once, and that would be that. But I'm sort of switching back and forth between the code editor and the notebook, so please don't change that file name. So that's the new thing, is this exporting a table into TF record. And the same thing on the image. Will we see a TF record thing there? No. So you don't see the TF record thing on the image, but it will export to a TF record file, and it may export the image in multiple pieces in different files. And we'll talk more about that later. But everybody...
Is there a link for loading these now, or do we have access to these right now?
So this is just a code editor link
Yeah.
from the notebook.
Oh, it's from the notebook.
Yes.
And real quick, just to point out, the way that we're actually instructing the image export to TF record is a new directive, file format, and specifying TF record there. If you don't specify anything, the default behavior is just to export to TIFF, and if you don't specify any format options, the default behavior is to do what it has always done. So if you specify file format TF record, that's when things will change.
So, right. There is some new stuff here. We'll cover this new stuff in a little bit. But for now, just run these exports. And by the time we get there, they should be done. This took about 4 minutes for me. So, any questions about the exporting from Earth Engine part?
Should we export it in a specific folder or just
Yeah, just into your Drive account, yeah. Okay, so everybody has clicked this link and run the image export at least. And now, because I've already done this, I have these files. And this is the file ID that is linking to the export that I made in my Drive account. But those exports are shared with the group. So if you have joined the group, you should have read access to the N. Clinton versions of those exports. And you shouldn't have to change this ID. The point that I'm making here is that that is the file ID like you would use with a fusion table. You know, you get the file ID and you copy it into your code. That's the file ID from Drive. And now what we can do is run this cell. And what we should have here is that we've been able to download the training and testing files. So in Earth Engine, I just partitioned the data with a random column. And I put 70% into training and 30% into testing. And at the end, we run an !ls, which will do a listing of the directory of the virtual machine that's running this notebook. And you should find a testing and training TF record file in there. Is anybody able to get a training and testing file? Good. Okay, so now we've got training and testing sitting in the working directory of this notebook, and we can start doing TensorFlow stuff. And the first thing that we want to do is we want to read those TF record files into a TF record data set. And that's easy. All we have to do is call tf.data.tfrecorddataset and give it the name of the training file and tell it that it's compressed. And at this stage, if I run this code, what we should get is this not necessarily human readable printout of the first thing from that file. So this is a coding idiom that I've found useful in debugging my TensorFlow programs, is sort of just running the first thing to see what's in there, much like you would do in Earth Engine when you say print, collection.first or something like that. And again, this is not necessarily human readable, but the point is that you can read from this file without error. Okay? And what we have to do is we have to tell TensorFlow what's in there. And so specifically, we have a list of bands. This is right from the JavaScript. I'm just telling it what bands are in there, or what's in the table. I have a label, which is the land cover label. And I'm going to make a list of all these names. I am also going to define some columns. So these columns, which are specifically tf.fixedLength features, or fixed len features, whatever, which have a shape. So these are just one-dimensional things, float 32. And these are just instructions to TensorFlow for how to parse things out of that TF record file. So we have some names, and we're saying, okay, we're going to make a little dictionary where the names are the keys and the fixed length features are the values. And so here's making the dictionary, and you can print it so we can see what that looks like. I'll just run the cell here. Now we see in our dictionary we have the keys are the names and the fixed length features are the values. And that's enough information for TensorFlow to parse the stuff out of that TF record file that we made in Earth Engine.
And just to point out, the column names match the bands in the image from which you created your export. So you'll get these band names out, and that's how TensorFlow knows which bands you're referring to.
Yes?
Do I have to get exactly the same number of bands or the same exact names? I mean, is it
Just the names.
You have to get the same names for sure.
so the file contains the names, but I just need to tell him the names as well?
You're just saying, so in that file, so Chris, you might want to bail me out here.
Yeah, sure.
In the file are, there's data and there's labels for the data, and you're just telling TensorFlow how to pull all that into a dictionary.
Yeah, basically you're just telling TensorFlow which bands you want to use, right? If you don't specify anything, it's not clear. So there are a lot of cases where you want to create this export, and you're maybe going to train your model on a small subset of the bands in that file. And this is the mechanism to do that, is you just specify the band names.
Like the select you do.
Sure, exactly.
So again, I probably should have had this as one variable in the Python that fired off the Earth Engine, did all my stuff in Earth Engine as well. And then I wouldn't have had to, hard code this way from the JavaScript. But, I wanted to go back and forth with the code editor. So this is just telling TensorFlow what you want to get out of that file. And here's a dictionary that's a set of instructions for how to parse this thing. And so what we want to do now is make a parsing function. And here's how this parsing function works. It takes this serialized example. Okay, so now I have to go into my little terminology dance here. Sorry for this. Examples in TensorFlow are features in Earth Engine. So like a single record of the file is an example, which corresponds to a feature in Earth Engine. But a feature in TensorFlow is like a predictor in Earth Engine. Sorry? Or a property, yeah. A feature is like what you are using as input to the model. It is not an EE.feature. So I'm going to be speaking in TensorFlow parlance today, in which case an example is a single instance in machine learning terminology, or a record from that file, and each example has several features, and the features are like what the inputs are to the model. Okay, so I'm going to run this, and now, okay, so it parses a single example. It takes this serialized example, it parses it according to that dictionary that we defined a second ago, and then we're just going to return the features and then the label. Okay? And what you do is you map that parsing function over the data set the same way you would do a map in Earth Engine. You map the parsing function over the data set, and now we're just going to print the first thing and see what it looks like. And what it looks like is a new dictionary in which we have the same names, but now instead of placeholders, we have data, tensors that have been read out of that file. Any questions about that? This is all just plumbing. Okay. At this stage, we have we've sort of exercised these parsing functions and looked at what's in that file. And what I want to do is I want to make some additional functions to create some new features. So the fancy machine learning parlance is feature engineering, but this creating normalized differences, I think that's not necessarily feature engineering. That's just something that we do. And why would you want to do this here? The reason I want to do this here is because let's say you train a model and you decide that you know, this is a crappy model, this is not doing what you want additional data or something. What you don't want to do is go back to Earth Engine, compute normalized difference, add it to all the points, do the export again, write a new parsing function, you know, all this kind of stuff. You want to just export your stuff once and then be able to make whatever features you want in terms of normalized difference on the TensorFlow side. So this is how you make these kind of features on the TensorFlow side. And this is just basic arithmetic with tensors. And the only thing I'm adding here is you know, kind of a silly little thing to deal with divide by 0. And that's it. You just make a new feature called NDVI, and you add it to the dictionary. Okay? So you have to run this.
Nick, I got a question.
Yeah.
So when you look at that tensor, right, the one that you just had where you had the B driving the values and so forth,
Mm-hmm.
and in Earth Engine you have, this is, I'm assuming is connected to one of your points that you put in,
Mm-hmm.
right? And that point has some sort of land cover category or class.
Mm-hmm.
Where is it in this tensor?
It's at the very end. So this thing is actually, Chris, what is this, a tuple or a list? I think it's a tuple.
Some Python thing.
I think it's a tuple. Anyway, here's the land cover label. And note that that one has the label 0, which is bare land, and it's an int32 instead of a float. Okay, so we made our functions to add additional features. Again, features in the TensorFlow parlance. And now we can put it all together into this input function, and it looks like it just fits on screen. And so the first thing that we do, we're just kind of putting together everything we've done so far. We load the TF record data set. We map the parsing function over it. We map our add features function over it. We're going to shuffle it. And batch it and repeat it for as many epochs as you want. And the reason that I have these, the number of epochs and the shuffle and the batch size is because you might want to do something fancy at some point in the future, like use those as hyperparameters and optimize your model by tuning those hyperparameters. And you can do that with stuff like Cloud ML, which will do this very nice hyperparameter optimization for you for a price, of course. But the reason I'm showing you this is so that you know how to do that.
Another good reason you might want to do that is you want to reuse this parsing function here. So if we're going to run an evaluation on our eval data, we don't really want to shuffle anything, right? We want to get consistent results every time. So this way you could just pass in the same function with shuffle equals false and get the same thing.
Right. So something important to remember here is that there's some randomness built into all this. And the other thing that's kind of new, if you've been doing this the Earth Engine way, is that you might want to reuse this training data set several times. You know, one time is one epoch, and we're going to specify a bunch of different epochs, or you know, several epochs. You'll see in a second here. So run this code cell, and at this stage, we can make a classifier, or what you know, a machine learning algorithm. Us old people still call them classifiers. Yes.
Could you also put parameters for dropout rate and things in this part?
Chris, I don't know the answer to that.
Would you also specify dropout rate at this stage? Things like other.
Yes, so you're talking about a dropout layer. This is a little bit different. So this is a canned model completely. So you don't really have the option to add a dropout layer when you're using something like a DNN classifier, which is, again, this built-in estimator thing. In a little bit, we'll look at a section where we're completely defining our own model, and that will be where you add a dropout layer. Yep.
Thank you, Chris. Okay, so let me just let me go back to the slides for a second here before we talk about training this model. Here's what we have. We have an input function. This is just an example from the docs, so ignore these names here. we have an input function that's returning a dictionary in which the names are keys and the values are, the keys are names and the values are tensors that have data, training data in them. And now, when we define the model, we want to tell the model which features we're going to use. And we do that by specifying feature columns. And so we're saying, yeah, we're going to use these are all numeric columns, and these are inputs to the model. And then so that's telling the model what features you want to use. We're also telling it how many hidden layers we want and how many nodes in each layer and how many classes and so forth. And for those of you unfamiliar with neural networks, here's what I mean by that. We have an input layer, which is coming from those feature columns that we've specified. We have some hidden layers, and I'll show you where that is in a second, but each hidden layer has a number of nodes. And then we have the output layer, which is going to be our prediction. So here's where that's happening. First of all, here are my columns. These are numeric columns, and these are just the name of the bands, including the new band that I made, which is NDVI. I'm specifying a learning rate here of 0.05 and an optimizer using that learning rate, and you might want to fiddle with that. So this is it's specifying how you want to train the model. And there are a variety of flavors of this kind of, from the garden variety gradient descent to fancier things, and that's all I know.
Another way to look at it, it is the algorithm responsible for reducing the loss in your model. And when we're using this DNN classifier, the loss function, if I'm correct, is already built in, or do we specify that later?
The loss function is built in.
Okay. So in this case, you won't actually see the loss function, but the optimizer's job is to reduce that.
Sorry for this question, but what is the loss function?
Loss function is comparing your, at least in this case, in supervised classification, and we'll again look at another version or example, is the, I'll say, accuracy between your predictions and the actual class labels that you have for the inputs. So you would expect a high loss function if a 1 was expected and you predicted a 0. You would expect a low if it was closer to 1.
So if the class matches the prediction, the loss is 0, and if the class doesn't match the prediction, then the loss is 1, something like that is a real basic example. So we have this learning rate, and again, you might want to tune this thing. I'm specifying 3 hidden layers here, 5 nodes, 7 nodes, and 5 nodes, and you might say, Nick, where did you get those numbers? And the response is, these are my lucky numbers, and that's it. This is not a scientifically valid approach. So, I fiddled with these numbers, I fiddled with the learning rate, and I fiddled with the number of epochs that I used to train the model until I got an accuracy that was reasonable. And again, if you want to do this the fancy way, feel free. You can tune all these hyperparameters, and you can use Cloud ML to do that if you're willing to pay for it, or you can do it on your own machine.
What was the epoch again?
The number of, one cycle through the training data is 1 epoch. So I'm training the model 8 times with the same training data set.
The question about this DNN classifier, so it's just, this is what loads existing model and transfer learning to, like when it specifies a scheme, specifying the layers.
Yeah, this is just a deep neural network in which you can specify the number of layers and the number of nodes in each layer and how you want to optimize it. And I don't understand the question. So these are the layers, and the number of nodes, the number of neurons in each of these layers. I have 5, I have 7, and then I have 5 again. And it's all fully connected. Yes?
This is not
No,
This is
usually-
creating a new model. We're just defining the structure of this network.
Yeah, it's a topology that we define, and then the weights are not used from any other existing model.
In this 8 epochs, is this that you run 8 times over your training set? Is this related to also the randomness you defined before? So in that case, it has to be random, and you are, if you wouldn't have put this random, it wouldn't make sense to have the 8 epochs.
Yeah, yes,
Chris.
more or less. There would be, right. So you would be effectively training your model to, right. So if there's a run of specific inputs and that wasn't shuffled, then that would sort of break some of the requirements we have for gradient descent. So yeah, you do have to shuffle the data.
So, following on the previous question, I mean, I guess is there a way to take a model that was trained by somebody who knows how to do this thing, land design cover change, trained model, and put another layer and retrain it?
Yes, you're talking about transfer learning. Yes, there's a million and one ways to do that. We are not going to cover that
But
today.
it's possible.
Yeah, very. Yes, quite.
So, in fact, Google is, there's a, sorry.
It's not a good question. You should not normalize all of those ones.
What do you mean by normalize?
I don't know, putting -1, -2, 1.
Well, you know, these are already 0 to 1 because they're reflectance. And yeah, I could have done something with NDVI, but you know, this.
Between the inputs, unless you're doing something like batch normalization, which is a little bit more advanced than what we're trying to cover here. If you have value between 0 and 1, that's already, yeah, that's a pretty nice range for weights in the model. And you don't have to have a layer that's specifically learning to reduce your 0 to 255 or whatever range into something that's more manageable. So in this case, if it's between 0 and 1 for each input, that's totally reasonable.
If you wanted to put something like elevation, your model would be turning everything into 600 deviations.
Yeah,
Like, you know,
what-
if you're using something like unit circuit,
Yeah, so if you wanted to use something like elevation,
does that happen inside the TensorFlow?
okay, so it's a difficult question to answer. So yes, so if you did not actually normalize something like elevation, what would end up happening in the model is the model would learn to actually reduce that to a range that could be used to compute values with the other inputs. However, that is using neurons that could be basically transforming your data in other more useful ways to do that normalization. So it helps to just engineer your data beforehand and maybe bring it into some range. Like maximum is 1 and then the minimum is -1 or 0 or something like that. Yeah, totally.
So, you might say, Nick, I don't like your model, you know.
Over there.
In some examples, you see them normalizing to -1. Is that just a style thing? Or?
Yeah, the question is, when do you choose between 0 to 1 and -1 to 1? Yeah, there's no great answer. Easiest way to put it is keep it consistent. So if everything's going to have a range between -1 and 1, do that. Don't mix and match things.
Okay, so let's continue forth. You know, again, I'm not claiming that this is the right way to build a model. I'm just trying to give you the flexibility to build models on your own. You can use Google's super fancy prepackaged models, which is from a product that I forget the name of, or you might find some incredibly brilliant TensorFlow land cover person who has already built a model for you that you can use, but I am showing you how to do it in case you would like to build them yourself. So this one is totally arbitrary based on some ideas that I had. You click run, and oh, I just clicked it twice, so it's trained it twice. Well, 16 times actually on the same data set. Everybody should be able to run the model and get an answer here. And at this stage,
Nick, can I ask just a quick question?
Sure.
Can you scroll up a little bit? So if you're doing this a couple different times, just playing with it, are you looking for a smaller value for that loss or final step yours says 0.42?
yeah, loss should be smaller, but never mind that. What we want to focus on is the evaluation of the classifier. So you might say, Nick, I don't like your model. This is not a scientifically valid model. And but you know, my philosophy on that is that the proof is in the pudding. And if you have a good number on the validation, then I'm claiming that my model is just fine. And by just fine, I mean the accuracy is around 87%. And some of you might get higher or lower numbers. You're welcome to retrain the model, so I can just run this cell again and train it another time, and then we can evaluate it again and see if I gained anything there. So now it's 94% approximately, and I'm quite happy with that, and I'm ready to move forward.
Just a heads up, Nick, we have almost 30 minutes left.
Hmm?
We have almost 30 minutes left.
Yeah, I'm gonna speed it up here. Okay, so at this stage, we have a trained model. And what we want to do is we want to use this model to make predictions. So specifically, what I'm going to do here, and I'm just going to run this so you can sort of see it happening. I ran the model. I said classifier.predict, and I gave it the input function using the test data set. And now I'm just iterating over the list of predictions that comes out. And the first one that comes out is the class label, but you also get probabilities for each class, which is a new thing that you could not do with existing classifiers in Earth Engine. So that's a new feature here. And at this stage, I want to write those into a TF record file. And this is just a demonstration, which I'm going to just go over real quickly, of showing how you build an example. So this is just an example proto, and it's got a prediction, which is just a 1. You know, this is all just for demonstration. This is garbage data. These are not real numbers. It's got a prediction, which is 1. It's got some probabilities, and you can write those, and then you can read them, and that is just exercising reading and writing from a TF record file. So this cell, which we don't have to run, is just writing those predictions that we just made on the test data into a TF record file. We don't have to do that, so skip. What we do want to do is classify the image that you exported previously. And here is where we are finding that file in your Drive account. So if I run this, and this is looking in my Drive account now, and it's finding these files, and there should be 2 of them. Okay, I see 2. This one is 001, this one's 000. Those are sitting in my Drive account. You should be finding your image files in your Drive account, but they should have the same name. Here's where I meant, you know, don't change that name because you're going to be looking for that later. So I have 2 files, skip the cloud storage thing. We are now going to write those into a TF record file. The difference between between what we did before and what we're doing now is that now we have a patch width. And recall, from the Earth Engine code, we have a patch width and a patch height, and you have to know those numbers. So here, when you did the image export, you specified these patch dimensions. And you have to know that. You have to know the shape of your data, because now we're going to use that shape of data when we do prediction on the image file. So here's the difference is that you have a patch size here, which is based on these patch dimensions. And now we are making lots of little tensors from our 256 by 256. We're making lots of little tensors from one big tensor, which stores a patch of 256 by 256 pixels. So you run this, and that will be able to read the image file. And now we want to say that we're going to write it somewhere. Oh, and you should specify something here like foobar or something. I don't know. Don't use foobar because I just did. My username is now foobar. And so it's going to write into this temporary bucket. And do not use that temporary bucket for anything. I'm going to delete everything that's in there at the end of the day. So don't store your 5 petabyte data set in this cloud storage bucket, please, because I will delete it. And now we can make predictions. So I'm just going to run this, and now it's using that new input function with the patch dimensions in there, and you have all the code, so you know how to do that with Earth Engine now. And we are writing it to a TF record file, and I want to write out the class, the predicted class, but I also want the probabilities to come in there. So what you should see here is that it's now writing patches, slowly writing patches. There are exactly 96 patches in this data set. And I know that because when I did the export wrote a little sidecar JSON file that specifies the coordinates of things and the patch dimensions, and we're going to reuse that JSON file when we upload the stuff back into Earth Engine. So that JSON file contains instructions for Earth Engine of how to reassemble all the TF record predictions back into an image. So it's writing this stuff ever so slowly, and when that's done, I'm going to copy. So it's writing directly into that cloud storage bucket. And all of you, because you're in the group, right? You are in the group, and therefore you have write access into that temporary storage bucket, so now you are writing your own predictions into that cloud storage bucket. We just want to copy the JSON file from your Drive account into the cloud storage bucket with the same name. And the curly brackets there are just so you can pull variables out of the Python and into the bash command. Okay? And I'm sort of, I'm jumping ahead here because it's still writing patches.
Can I ask a question about something previous?
Sure.
So this time. Well, you actually said that this is the new feature that before was not in engine. Can you please repeat it?
Yeah, so the new feature is the new feature of Earth Engine is reading and writing TF record files.
What was about iterability or something like that?
The new TensorFlow feature, which is letting you do things that you couldn't do before, is having those probabilities for each class. Yeah. Yes?
Can I also ask something about previous thing?
Sure.
When you mentioned you were not satisfied with the result of the training, in some case it was, I don't know, 80% or it can be 60 and then it can be, so you rerun until you're satisfied. But to me, it sounds more like it's not really robust. And why would you be more satisfied with a result that is 90%? Because it might just depend on how your training and your test set was divided, and you're not certain that your result will be better on your image using the 90%.
Okay, so the question is, how do you optimize your classifier, and or optimize your classifier given your training and testing data sets? And the answer is that is entirely incumbent upon the user, is to determine the efficacy of your training data to create an externally valid classifier. And I'm claiming that for the purposes of this demonstration, my training and testing data are just fine, and I can train it and get 94% accuracy, which may or may not be better on the image data set or some validation data set that you have collected in the same area. I don't know.
And just to sort of maybe be more concrete, so we are evaluating on data that our model has not been trained on, if that wasn't completely clear.
Okay, but it might be just a coincidence that the 90% is now better on this particular training test set.
Right, and the certainty of it being a coincidence or not diminishes the larger your evaluation set grows. So then what Nick said totally applies here, in that this is up to the evaluation set and how well that would reflect an actual set you would form predictions on, in this case.
When was this JSON file created?
When we exported the image from Earth Engine.
So that should happen automatically.
Yes.
The image export already puts it there.
When you export an image to TF record file, you also get the little JSON file. Okay, so we're almost done here. Let me just skip ahead a little bit. We're just copying the JSON file back into the cloud storage bucket, so it's alongside the image files. The next thing that we're going to do is install Earth Engine. So somebody was asking me about whether Earth Engine was here by default. It's not, but you can easily install it. And let's see, patch 95, patch 96. Hopefully that will be the end of that, and it is good. So now I'm just going to copy the JSON file. I am copying the JSON file, good. And now it's listing this bucket, which has all kinds of stuff in it from lots of users now. And that's okay. Ooh, look at all those fun files. And now we're installing Earth Engine. And we're going to do the same authentication dance that we did before. So at the end of this, it's going to say, go to this link. And I'm going to go to this link, and yes, it's me. And now this is to give Earth Engine access, and or to give you access to Earth Engine. So I'm going to copy the code, and I'm going to paste the code here where it says your code here. So paste that there and run. And that will now authorize you to use Earth Engine. And so now we can do stuff like check the upload command for Earth Engine. And so we now have the Earth Engine command in our virtual machine. And I just got the help for Earth Engine upload. But what I want to do is I want to upload those files into my asset folder. So I'm gonna copy this. I am N. Clinton, so I can use this. Of course, you want to replace this with your own username, and I'm going to call this TF foobar predictions or something, and run it. And now this hopefully will, okay, so it says it started the upload, and now I can import the Earth Engine library and look at my tasks that are running. And specifically, I see that there's a task that's ready, which is uploading my foobar predictions. And I'll just run it again, and now it's running, and that should be done pretty soon. But I have already baked the cake for you, and I just want to show you what those files look like after I've uploaded them. There are my predictions, and there is my probability layer. So this is not different. This is not substantially different from anything that you can do with existing classifiers in Earth Engine. Right? Just a predicted land cover map. May or may not be better than random forest or any of those other classifiers. This is something that you could not do before. And so that's the new thing. But again, this is all very basic per pixel classifications. What I'm demonstrating here is really just this workflow that lets you integrate all this stuff together. Did anybody successfully get their own classification into Earth Engine?
96, I think.
96. That's good. Okay, so while that's running, I'll turn that over to Chris, who's going to give you the real goodies here.
Well, I hope so.
Take it away.
All right, thank you. Okay, so pick up exactly where Nick left off, and with the question, not even the question, but the observation that this is, what we did here is nothing different than what you could do in Earth Engine's existing classifier framework. So, other than getting class probabilities, why would we actually want to use TensorFlow in the first place? The big deal is we can start to get spatial, and we can start to consider the spatial context of a pixel, and we can start to consider the temporal context of a pixel. So before we're looking at these classifiers that are focused on some combination of the bands of a single pixel, but that doesn't include the bands over time, and nor does that include the bands surrounding the pixel. So we can start to make much more informed decisions when, say, two pixels have a very similar spectral signature, however, they're referring to two different classifications, even land cover, in the case we were looking at a moment ago. So to go quickly, what we're going to do today is we're going to look at an object detector using TensorFlow. This is something you could not even begin to do using the existing classifier API in Earth Engine. It's certainly not per pixel classification that's present in anything similar. So Again, this is where we're going, okay? Real quick, I want to briefly talk about the kind of things we're hoping you guys will start to do with TensorFlow and these new Earth Engine integration features. The first thing is something quite similar to what Nick just did. While Nick's example was confined to a single pixel, there's no reason you have to do this. You could be striding a model over a region, which is exactly what we did. We took a patch of pixels, we cut the bands out of each pixel in the patch, and then applied a model to the bands in that pixel. There's no reason your model couldn't be a spatial model or a temporal model. Recurrent neural net, convolutional neural net, or any dense net that's effectively the same thing. So the other thing that we might be doing is creating fully convolutional neural nets, which is something we'll do in a second. I'm not going to go into the gritty details of what that is, but essentially this is a much faster way to effectively do the stride model over a patch of pixels technique. Another thing we talked about before is we might be interested in the temporal context of a pixel, in which case you might have something like a recurrent neural net. One of the examples of proof of concepts while we were working on these features was actually a precipitation predictor, which was examining the certain things like precipitation over time, temperature, humidity of a single pixel, and then with 53 weeks of data, let's predict the 54th. So these are the kind of things you could never begin to do with something like random forest. Just to be clear, this is a image, or at least the animation of convolution, but it also serves as an animation for what it looks like to stride a model over a patch of pixels. You guys, probably most of you are aware of what convolution is, but if you look, we're essentially taking this model of weights, you can imagine it's a small neural network, and striding it over the source data to produce some predictions. This is also a convolution, which is relevant to convolutional neural nets. So these are things that are very similar, and at least producing 2D data.
Just out of curiosity, how many folks in here are unfamiliar with the term convolution? Okay, so a couple.
That's a couple. Cool. Yeah, so
You're taking a little window and you're sliding it around, and everything in the window is now the input to the model.
right, you're multiplying weights by the input and then adding those together to get the result. Okay, so real quick, again, I don't want to try and cover the details of a convolutional neural network, but the idea of a convolutional neural network is in that convolution, this thing we looked at a second ago, you'll see there are weights in this kernel, or we also said it was something like a model. And in the CNN, we let our neural net learn those weights. So for those of you who are familiar with convolutions, you've probably heard of like the canny edge detector, right? Which is a certain kind of convolution with weights that highlight edges in the image, or produce a strong signal for edges in the image. What we're going to have a convolutional neural net do is actually learn these edge detectors and these feature detectors. And this is a really powerful thing once we start to stack these. We can learn edges, textures, object parts, and just proceed with more and more complicated object classes. Not something I also want to get into heavily, but we can expand a convolutional neural net into something called a fully convolutional neural net. Objectively, these neural networks compute the very same kind of predictions as each other. The difference being, this is relevant, we won't go too much into why right now, is that a fully convolutional neural net does not care about the scale of the inputs. Whereas a convolutional neural net would like to give you a class. This is a picture of a cat, this is a picture of a dog. A fully convolutional neural net will take a region of pixels in an image and mark them as cat-like, or dog-like, or car-like, as we'll look at in a second here. Okay, real brief here. Let's look at the workflow for this object detector that we're going to run with Earth Engine data and TensorFlow and Collab. So what we can do is we can annotate a bunch of examples. In this case, we'll annotate a bunch of cars. And then we can export that training data. We'll be sampling the car-like region. We'll train the model on these chips. If some of you are familiar, the term is called chips when you have a label and then a region surrounding that label as the input for that label's class. So we train it, then we'll export the inference data. Okay, cool, so we have a trained model that can understand a pixel and provide some, or excuse me, a region of pixels and give some prediction as to whether that pixel is car-like or not. We'll apply that concept to an entire region. So now we'll produce a heat map of hot, as in very car-like, and cold, as in not very car-like. We'll run our predictions, and the last thing we'll do is we'll use the image processing features of Earth Engine to turn that heat map into something useful. In this case, vectors showing us where cars are and where cars aren't. Okay, at this stage,
Yes.
what's the thing to get us into the...
You Windows people.
Yeah. right, sweet.
This guy?
Yeah.
Should I just get it?
Yeah, let's do that.
Actually, I think I can go like that and like that. So in the speaker notes of the slides is the link to the fancy car detector notebook.
Yes, this should be shared with all of you guys if you join that group. If not, it's not super important. We have 15 minutes, so I'm going to kind of just be proceeding through this, whether or not you guys are following along or not. But you do have access, so you can do this yourself. Just give me one moment. I'm going to connect here. Another thing I'd like to do, I'm not going to run all the predictions and the training here. Training, so Nick's model is able to train in a matter of seconds. This model takes about 20 minutes to train. We have way more weights, much larger input set, and much larger, much larger number of layers. So I'm just going to authenticate here real quick. Let's see how badly I am with a Mac. And we're just doing the same thing we did a second ago. And this is only because the runtime is switched because we opened a new notebook.
Here, you want me to?
You want to? Yeah. We'll do it quicker. Dope. Okay, cool. All right, so let's really quickly, we saw that diagram before of the steps we were going to go through to create this object detector entirely in Earth Engine and TensorFlow. Let's look at a couple notebooks that'll sort of break this down. Okay, so the most labor-intensive part of supervised classification is creating the training data, especially if you're doing it by hand. In this case, it was, let's see, outlining 1,000 cars in about a 1 kilometer block of Mountain View. And if we zoom out here, you can see we painstakingly outlined all of these cars.
What poor sucker did that work?
Yeah, I feel bad for it. So again, this is something we can do in Earth Engine. There are tons of data sets that are available online, but we're showing you geometry tools in Earth Engine to actually create these annotations ourselves. Okay, cool. So we now have this vector mask of pixels that are car-like. And then we can draw a box around this region and then use a vector subtraction to now create a region of pixels that are not car-like. So we have this car-like mask and this not car-like mask. And we're going to use this to generate our training data. So I'll now open up this next Earth Engine notebook. Just proceed quickly here. Not going to dig into the code just for brevity's sake here so that we have time for questions. We're going to take the same block, the same, well, it's not really a block, the same square kilometer here, splitting it into 4 regions. We have our training side and our evaluation side. We're splitting the data sort of as harkening back to a question earlier, so that we are never evaluating on the same set we trained on, because then we're not actually gaining anything there. We're just learning that, yes, we did see that training point. Another thing I'll point out here is there is actually also a further split in each training and evaluation region. That was simply because there is a higher density of cars in parking lots in the upper half of this kilometer square, and fewer cars in the more suburban environment, so I didn't want there to be a bias in the training data towards cars that were on tarmac and non-permeable surfaces. Okay, cool. So actually, let's just go back to this real quick. Something we're going to do here, and I do want to point this out, is another new, or semi-new feature of Earth Engine. How many of you are aware of neighborhood to array in Earth Engine? Okay, a handful of you. So, so this with neighborhood here, I'll just kind of point this out real quick. This is the way we're going to extract what are known as chips from these random points in our training and evaluation sets. What neighborhood to array does is it takes every pixel in an image and converts that pixel to its own neighborhood. So if we were to inspect a pixel in an image for which we've called neighborhood to array, each pixel would be an array pixel of 61 lists, each list of length 61 in this case because we have 30 by 30, which seems a little insane, but because of Earth Engine's lazy evaluation model, this doesn't end up actually generating 61 times the number of images when you do it. But anyway, neighborhood to array is how we're actually creating chips from these features, these points. Okay. All right, so we're going to do something very similar to Nick's example. We're going to define some feature columns, being a little bit more succinct here, just to kind of breeze through things. We're going to find, remember, our input to our model is actually a 2D tensor. So we're going to define, we have side defined up here, and we have 4 different bands here, red, green, blue, and luminance. Why we are bothering with the luminance feature, we'll explain in a second. Also, this is something that you could engineer yourself, as Nick did with MDVI. We also have a class label. which will be 1 or 0, 1 being car-like, 0 being not car-like. Again, our goal is to generate a heat map here. We're going to parse the data. Also, great. Another question was about, how do we shape our features if we have something like elevation and its scale is vastly different than the scale of the other features. What we're doing here is we're actually going to divide all of our features by 255 because these are RGB values, and now everything will be scaled between 0 and 1. So our neural network can spend less time trying to normalize these values. It can instead be applying these transformations to figure out whether it's a car or not. Map, shuffle, batch, things we've already talked about. Okay. I'm not going to speak too much on the model, but before, remember, we had that DNN classifier, which was this canned model that TensorFlow comes with if you really just need n number of layers of depths. You don't always have to do that. Instead, you can specify your own model. And here we've specified this FCNN, this fully convolutional model. I've tried to put a whole bunch of comments in here so you guys can take a look afterward and see exactly what it's doing so you can generate your own. Also, somebody asked a question about dropout layers. This is the place where you would actually add the dropout layer because you're defining your own model. Here we've added a dropout layer or right before the final linear layer. Cool.
Is anybody able to see this notebook? Okay, good.
Yeah, cool. Last thing I'll say about this model, immediately after saying I wasn't going to talk about it, is the last step here. So, brief word on convolutional neural nets. So, a common operation, if those of you who aren't familiar, in a CNN, is to reduce the dimensionality of the data. So, you'll apply one of these convolutions, right? We talked about these things, learn these filters. You'll apply one of these filters, but if let's say you apply that to a 256 by 256 image, you'll recover a 256 by 256 image, and that's not getting you any closer to a classification for any pixel, more or less. So what we'll do is something called a pool. There's more complicated reasons for that, but we'll do something called a pool, which actually reduces that 256 by 256 image down to something like 64 by 64 or 128 by 128. There's things like average pool, max pool. You can imagine what we're actually doing. We're sort of, again, reducing the dimensionality of the image. Why that matters? Why am I even bothering to say that? That's because if we feed our model a patch, let's say 256 by 256, the output from that model is not going to be a 256 by 256 patch. It's going to be something smaller. What we want to ingest is that full-size patch. Standard practice for a fully convolutional neural network is to do something called a transpose convolution, where you actually learn the reverse of a convolution, and you blow your model back up, and there's all sorts of ways to do that, and connect certain parts of your network and forward feed them to these things. Way too complicated for our purposes. We're literally just going to bilinearly scale that reduced image back up to 256 by 256. I want to explain that because you will see this later and wonder why our model includes image.resize. This is why. This is our proxy for our transpose comp-up. Okay. Next thing you have to do, and I also want to mention this, remember the estimator we were using in the last example had everything baked in. If you are generating your own model, you also have to define how the estimator will work when you're training, evaluating, and predicting. That is the whole point of this model function here. This is returning this concept of estimator specs, depending on which mode we're in. And again, I don't want to get too much into this. This is, again, just going to tell the model what to do when we're training, evaluating, and predicting. Okay, and just so that I can show you guys how fast the predictions happen, because that's actually pretty cool. I'm just going to run these so that our notebook has a sense of what we're doing here. And you guys should all be able to do this because you have access to the bucket that stores the trained model here. All right, we don't need to train it. We could evaluate it. So again, this is going to take longer because we're evaluating on actual pixel patches, and it's a much deeper network. So we give it just a second here. Okay, in this case, we're getting 0.996 accuracy because this thing has been trained a million times. Okay, so let's look at the last part. All right, we have a trained model. It's an FCNN. I know I've been going really fast here, but thank you for bearing with me. We're at the final part where we're going to actually generate our predictions from our model trained on those chips that we went through that whole process of random sampling and neighborhood to array. So I think you guys get the idea of how export to image works. I'm not going to bother to open that notebook. But, okay, we're going to define one more input function. You guys have seen 3 of these today. Remember, we're defining columns, these fixed length features. These can be sparse features, a million different kinds of things. But we're using fixed length features because we know their size when they're coming in. Same shtick as last time. We're going to divide them by 255 to normalize them, make an iterator out of them. Just have to run this concept of what we're doing here. Also, as Nick briefly touched on, to actually re-ingest these predictions, we actually have to build some TF records in TensorFlow. So we're going to be, right here in our example, this make example function, creating examples such that in Earth Engine, when we're done, we'll have a band of class IDs in our image and a band of probabilities. Again, this probability being a new thing that we can start to do in TensorFlow, among many other things. Okay, cool. I'm not going to run the export because the export takes like 10 minutes. We have these prediction files. Nick said you can get a bunch of prediction files. There's a bunch of prediction files. I will also mention there is, not specified here, but in a little bit, one of those sidecar JSONs that we also got with our export. Okay, so I'm going to hop into a cloud bucket real quick. Just to make sure I can do this live, I'm going to just delete the previous run of predictions so that we can do this here and now. Sweet. Okay, so remember how fast it went to predict when we were striding a model over a region? And then I posited that using a fully convolutional neural net for a similar purpose would be way faster. Remember, this model has orders of magnitude more weights. Input data is in 2 dimensions, and we have way more input data. And assuming, oh, I have to reconnect here, which might mean I have to rerun everything. It does. So bear with me, guys. Sorry, it just disconnected. Let's do this real quick. I know, I just set it up like it's going to go so fast, and then it just didn't.
Hey, Nick, can I ask a question while he's running?
Sure.
Those? So can you also look at the relative influence that the different input files are for your final predictions? You can see your probabilities of prediction, but can you see what was really useful to throw at it to get your results?
Are you talking about variable importance?
Yeah. So if you have, you have your Landsat for land cover, let's say you throw in some SAR data, can you see the influence that SAR had on your output?
I think the question is, can you use a neural network for variable importance or variable ranking? I don't know the answer to that. Does anybody know about neural networks for variable importance?
I think there is a random forest in TensorFlow. If you want to get something like that importance of random forest, which is what I wanted.
I guess that's a random forest thing. That's another one.
I've seen it in random forest.
Yeah, I know that with these neural networks, we can generate some kind of images highlighting which areas were more important for certain predictions.
Yeah, so that's
But
a
I don't-
good
but-
point. We're actually going to get to something like that.
Yeah,
in a
but I
second.
don't know if you can, well, I guess from that you can do something.
All right, so real quick, oh, go ahead.
I have done that with H2O with Collab. So it's possible to run this with Shadow, I don't know, but just depending on the colors.
Okay. So to push things along, all right, just pretend I did that really cool preamble and we got back to this again. All right, yeah. The last one was slow. Presumably this one should be fast, right? All right. Let's see what happens. Yeah, that's a lot faster. These are 256 by 256 pixel patches it is writing. So the power and speed of a fully convolutional neural net compared to striding a model over a region of pixels is immense. Also the fact that we can start to optimize an FCNN using the GPU that Collab, or whatever Python environment you're using, has. Again, you can't always use this technique, but when you're trying to generate something like a heat map, like we want to do for our object detection, or really just a classification map that, upon which you'll run connected components, this is a really useful model shape. Okay. Am I going to run this ingestion? No. You saw it happen a second ago. But we're going to basically do the same thing, and you can do this in the notebook at your own leisure. Okay, so we've done the same thing. We've generated these predictions. I'll just point it out again just to drive the point home. If you are ingesting from an export that you made for prediction, you have to include this mixer.json file that is produced with the ingestion. TF record does not really include any metadata. You could pack metadata into it, but now you're expecting things like your model and other file form, or actually other applications that could consume TF records to need to know that. So these TF records have no information about projection or even number between files. So that's why you need this this sidecar. It does not matter how many files you produce. If I wanted to produce a TF record per patch, or just a single TF record, it does not matter. What does matter, though, is that your predictions are named in lexicographic order, which is why we bothered to go 0005 instead of just 5, something like that, because then 15 would come before 5. Okay, we ingested them. Now let's take a look at the last step where we take this heat map, hopefully it worked out, and turn it into something that's useful for object classification. I'm just going to hide this so we can take a look at the code for a second here. So we can get rid of that. Okay, so real quick, the steps here is we're going to convolve the heat map, and that, again, was just to make it look a little bit nicer because it looks kind of blocky. But the important thing here is we're doing just a little bit of, I'm going to call it cheese ball classical image processing here. So we're doing kind of what we talked about, an erosion followed by connected components, right? Because we want to turn these connected areas of car-like pixels into actual detected cars. Reduce the vectors so that we can actually put a box around them, and then some nice visualization parameters there. And the result of that is, if we turn off the top layer, is we get something like that. And what we have done here is we have, you can see, so I'll just kind of point out some of the things to look for here. You can see the heat map is really what these blobs are. And that's what we've attempted to connect and reduce to vectors. And before you think this is really awesome, I'd like to point out things like this carpool symbol also turned into a car as far as we're concerned. Again, this model isn't super rigorous, and it takes about 20 minutes to train, so it's nothing, again, nothing super serious. But what can we learn, okay, from that? Yeah, it's kind of funny, but what can we learn from this model interpreting that carpool lane sign as a car? This can help us re-engineer the features we use to train the model. If we know that things like that symbol, and let's actually kind of cruise down here for a second, and we'll notice that these road arrows are also being interpreted as cars. So we now know that, okay, or at least we were getting a sense that these symbols on the road, help me, there we go, okay, cool, are very car-like. So what we might do is, when we're going back to generating our training data set, is go back and annotate some of these road signs, specifically annotate some of these with a label of not car-like. And then we would feed that to train our model, so that hopefully we don't wind up in the situation where we're actually classifying these. So yeah, that was a walkthrough of an FCNN.
One question, you said some of these features, how many input data do you input?
How do you choose how much training data you need?
Yes, yeah.
That's a really complicated thing to answer. It comes down to how fast your model trains. You can do things to make your model train faster and require less input data. It's also most strongly tied to the complexity of your model. The more weights in your model, the more weights need to be learned, and the more training data you need.
Generally, you need a lot of training data for these kind of models, but fortunately, you have Earth Engine, so
Yes.
it's easy to get that kind of data.
Actually, just gonna hit that one first, because he had his hand up first.
Yeah, well, congrats, it was impressive. Normally we don't look for cars, we look for clouds. We
Sure.
Go here, look for clouds. And clouds, the way as we human recognize a cloud, because a cloud is a shadow. And this shadow is like far away from the, the white thing, a black thing. So I was thinking about tweaking the kernel on TensorFlow, just to make a kernel which is like far away.
We were taking into that fact that the sun is actually projecting a cloud shadow below there.
So you can like reprogram some kernels that's, to recognize this thing. We can actually do
Yeah, that sounds actually super clever. I'd be interested to see what happens with that, because yeah, you could totally do that. You can do that in Earth Engine. You could just
You can
transpose the
treat
points.
the kernels.
Oh, well, you can do whatever you want with the kernels. I mean, if you have a convolution, you can set that up however you want. I think in your case, you would have two different data sets where you have the region that's been projected down to where the clouds are, and then, yep, and this is one set of input features. This is my guess of how you would do that. Yeah, cool.
Maybe use the sun, altitude, position to set that parameter.
You don't have the output of the cloud, so you need to
Go ahead, sorry.
Sorry, I might have missed it, but what is the rectangles in red you see, is this what actually was classified specified, or I see also the blobs. So what's the difference between when there is a rectangle around the car and when not?
And when there's just a blob.
Yeah.
So in this case, we have, okay, so I'll back up and try and more fully explain that. So if this were a model that we had trained in more than just 20 minutes or something like that, we would expect there to not be so much noise that we have around here, and we might not even have to meter the size of the connected components, which is the measure, which is how we decide whether or not we draw these rectangles around them. It's coming down to the size of the connected component. In this case, if this were not something that if we didn't have to worry about the noise of the model, and though often your models will be pretty noisy, so you'll have to do some sort of filtering of this output heat map or output class map. In this case, the choice was to just take, is the blob size this? We attribute this not to noise, and we'll draw a rectangle around it.
So just real quickly, those are false positives. If there's not a car in there, that is a false positive prediction.
Yes, but the just very simple. The rectangle, was it drawn manually or was it done?
Oh, this was done. This was all. I didn't draw any of
That's in Earth Engine.
Yeah, Earth Engine.
You can
uses
find the
vectors.
code that makes those rectangles in the Earth Engine JavaScript code.
When was decided to draw it or not, or how it was decided?
Yeah, so that, I'm just going to kind of this is what, so I'm just going to back up for a second. This was what the model produced.
Yes.
This is the output from the model.
Okay.
What we did is we ran connected component analysis on a thresholded version of this heat map.
In Earth Engine.
In Earth Engine. This was all done in Earth Engine. Then we reduced those connected components to vectors, and around each of those produced a vector.
Oh, and then you have the.
And then we just display a box on the screen.
Okay.
Yep.
Thanks.
We have time for one more question because we have to go to the next session.
Okay. What do you mean by actually creating the annotations? Depends on what your definition of
Can you get a TensorFlow model to create training data for you? Can,
so just to be more concrete, so what do you mean? So in this, we just use the geometry tools to kind of, what would it be, what would you say would be the preferred way of it?
Well, just think about how you might use geometry tools a bit more easier to work with, so you can put the labels in a bit easier way. There are some tools, Python tools and so on design.
So you mean focused on the annotations instead of just creating shapes and then adding it to the labels later?
that would be a great application of the UI tools in Earth Engine.
Well, okay, so what we're trying to do here is reduce the number of steps and number of applications you're actually trying to use. With this TF record export, not only in your Python environment do you only have to import a single package, being TensorFlow. That is sufficient both to write and read TF records from Earth Engine in TensorFlow, out of TensorFlow in Earth Engine. So you don't have to export the TIFF. There's no reason to actually open it up in any other application. Again, we're trying to reduce the number of, so now we've sort of got it in two Earth Engine and TensorFlow, and that should be sufficient to do.
It does kind of knock us into only using TensorFlow as a
Sure, if you wanted to use TF record, again, if you wanted to use a different framework, like Cafe, Torch, something like that, you're totally free to export as TIFF. And in that case, there will be an extra step for you. You could also export to CSV. This is something that's consumable by these formats, though a lot slower and not nearly as scalable. Yeah, again, TF record was sort of targeted because we can run TensorFlow. TensorFlow is highly scalable. Collab supports TensorFlow natively with that GPU environment. So it was the quickest way we could connect you guys to GPU powered in the cloud. Yes, because they are already formatted in a way that the model will innately consume, basically, because it's already a feature map, and you can already see, examples are already in sequence, basically, which is really easy for us to put back together into Earth Engine.